We're now going to begin our discussion of the next type of synchronization mechanism supported in Java. This is called barrier synchronization. In this lesson, you'll understand what barrier synchronization is, and I'll explain 3 different ways of using barrier synchronizers. We'll also talk about a human-known use of barrier synchronization that you're undoubtedly familiar with. The earlier discussions we've had on Java synchronizers have focused largely on classes that affect the behavior of individual threads. For example, atomic operations are actions that happen effectively all at once or not at all. Likewise, mutual exclusion synchronizers allow concurrent access and updates to shared mutable data without running the risk of incurring race conditions. And finally, coordination synchronizers ensure that computations run properly, for example, in the right order, at the right time, and under the right conditions. In contrast, this next type of mechanism is called barrier synchronization. A barrier is a synchronizer that ensures threads must stop at a certain point and can't proceed until all other threads reach this barrier. A good example is illustrated in this picture, which is a race with horses where all the horses have to line up at the starting gate to begin at the same time. It would be terrible, of course, if the horses showed up in some random order and as soon as they got there, they could start to run the race. It wouldn't be a very fair comparison of the horses then. Barriers can be used in 3 ways. Throughout this example, we'll use an image rendering engine as a running example in this part of the lesson. The first way a barrier can be used is as a so-called entry barrier. For example, our image rendering engine might want to make the concurrent computations for rendering the image wait until some object is initialized. For example, you can see here that the main thread spawns some number of worker threads, perhaps as many as there are cores, and then the main thread performs some time-consuming initialization of data structures. So it wants the worker threads to wait till it's done with that initialization process. To ensure this happens, the worker threads wait on an entry barrier, which in this case is called minitialization done barrier, until the main thread completes its initializations. Once the main thread decrements the entry barrier to 0, the various worker threads can then continue. Another form of barrier is called an exit barrier. For example, we might want to block a thread until a group of concurrent threads have finished their processing before allowing the first thread to continue. Using our image rendering engine as an example, here the main thread may want to wait on an exit barrier for all the worker threads to finish their computations. And as each thread finishes, it decrements the barrier count, which in this case is the conversion done barrier. And when that count drops to 0, the main thread can now continue. The third and final type of barrier is called a cyclic barrier. For example, a group of threads may all wait for each other to reach a barrier before they can advance to the next cycle. This barrier, the cyclic barrier, could use either a fixed or variable number of threads that run concurrently. At the end of each cycle, a decision is made about whether to continue or not. If the threads decide to continue, then they all can go on to the next phase, the next cycle. Otherwise, they'll all go ahead and finish. There's an interesting human-known use of barrier synchronization that you've probably encountered if you've ever gone on a tour with a tour guide at a museum. The museum tour guide typically follows various protocols, and the museum follows various protocols as well. From the point of view of an entry barrier, tourists may wait outside the museum until it opens or until a tour is scheduled to begin. So at the point when everybody's assembled, then the tour guide may say, okay, we're all here, I've got a count of everybody, now we can go ahead and enter as a group. From the point of view of an exit barrier, the museum may have a policy that it only closes, shuts down, turns off the lights, turns off the power, turns off the heating, whatever, after the last group of tourists leave. So as long as there's still tourists in the museum, they can't shut the museum down. So that's an example of an exit barrier. And the tour guide might also be responsible for doing that as well. When the last group leaves, the tour guide turns things off. You wouldn't want to have a situation where people got trapped in the museum after the doors were locked, after the lights were turned off, or the electricity or the heating and cooling was turned off. Likewise, there may be a cyclic barrier used if the tour guide waits for all the tourists to finish exploring a room before taking the group on the tour into the next room. So every time a group of people get done, they all gather back with the tour guide, and then they can proceed on to the next room. So they all kind of work together as a group to coordinate. And obviously they'll keep going until they're finished exploring the whole museum. Cyclic barriers can either be used as entry or exit barriers, but the notion of cyclic means that there may be multiple phases or cycles. Also notice that barriers can be used for either fixed or variable-sized number of tourists. And we'll talk more about this when we get into the details of how Java implements barrier synchronizers to see the way in which they support fixed and variable-sized numbers. So that's the end of our introduction on barrier synchronization.